Today, let us learn one of the most important theorem in number theory, that is Fermat's little theorem, which has got many applications and it is central to much of what is done in number theory. At least it can be a labor-saving device in certain calculations, and it is a tool in testing the primality of a given integer. Okay, Fermat was a trained lawyer making mathematics more of a hobby than a profession. Nevertheless, he made important contributions to analytical geometry, probability, number theory, and calculus. So let us look at Fermat's theorem. It says if P is a prime and suppose P does not divide A, then A power P minus 1 is congruent to 1 mod P. How it is? Let us prove this. Let us take first P minus 1 multiples of A. Okay, A, 2A, 3A, like that. P minus 1A. First P minus 1 multiples of A. In fact, positive multiples. Okay. First P minus 1 positive multiples of A. They are like A, 2A, 3A up to P minus 1 into A. Observe that none of these numbers are congruent to any other with respect to mod P. Okay. Suppose this cannot be congruent modulo P to any of this. Okay, you can check it out. Suppose if I give value of A as 2 and P as 5. Okay, suppose this is the case, then I'll take positive multiples of A up to P minus 1 up to 4. Okay, so first one A, 2A, okay, 3A, then 4A is 8. Now you look at these numbers, they are not congruent mod P 5. 5 here, mod 5, when I take modulo 5, they are not congruent to any of themselves, right? And none of these number is congruent modulo 5 to any other. And one more thing is they are not even congruent to 0 mod 5. Same here, these numbers are not congruent to any of these numbers only, or they are not even congruent to 0 mod P with respect to P. Okay, so you can check. Suppose they are, what happens, say suppose some RA is congruent to some SA mod P. Suppose RA is congruent to SA mod P, where R and S lies in between 1 and P minus 1. Okay, if that is the case, what happens? I can cancel A in the congruency relation so that I can write R is congruent to S mod P, which is impossible, right? I cannot write this integer is congruent to some other integer mod P, okay, which is impossible. In fact, that won't happen. Therefore, I can say the set of integers A, 2A, 3A, P minus 1 into A must be congruent modulo P2, congruent modulo P to which numbers? 1, 2, P minus 1. You can observe, in fact, in this case, okay, when I take this 6, suppose 6 is congruent to 1 mod 5. Similarly, if you take 8, then it is congruent to 3 mod 5, like that, right? So these numbers are congruent to 1, 2, up to p minus 1 when you take modulo p. Okay, I can write to this in some order. I don't know in which order. Okay, not necessary that a has to be congruent to 1 mod p. Okay, so taken in some order. Now I'll multiply all these congruences together. Okay, these I'll multiply and I'll take modulo p. So a into 2a into 3a up to p minus 1a. This is congruent to 1 mod p or 2 mod p, I don't know which. So I'll multiply all the congruences. Okay, so the result comes out to be p minus 1 mod p. Okay, now what does this? A is multiplied p minus 1 times, right? A into a power p minus 1, and the numbers are 1 into 2 into 3 into up to p minus 1, which is nothing but p minus 1 factorial. I hope you know the notation, factorial, and which is congruent to, now this is again I'm multiplying from 1 to p minus 1, which is nothing but p minus 1 factorial mod p. Right, I can cancel p minus 1 factorial because see, p does not divide p minus 1 factorial. Therefore, I can cancel them and I'm left with p minus 1 congruent to 1 mod p. That is what Fermat's little theorem says. I'm sorry. If p is a prime number and p does not divide a, then a power p minus 1 is congruent to 1 mod p. Slight changes to this, in fact, the corollary to this. If p is a prime and this division option is removed, if p is a prime, and then I can say a power p is congruent to a mod p. I'm just violating a condition, p does not divide say. I'm removing that condition from the Fermat's theorem. So corollary to Fermat's little theorem, it says if p is prime, then a power p is congruent to a mod p for any integer a. You can check it out this. If p divides a, then what happens? If p divides a, then a power p is congruent to 0 mod p. That is same as writing a power p is congruent to a mod p, right? And if p does not divide a, then Fermat's theorem says a power p minus 1 is congruent to 1 mod p. This is same as writing a power p congruent to a mod p, right? So it's not necessary that p should divide a or p should not divide a. Okay. Next is lemma, which says if p and q are two distinct primes, and in such a way that a power p is congruent to a mod q and a power q is congruent to a mod p. If that is the case, then a power pq is congruent to a mod pq. It's quite interesting, and this helps us in solving most of the congruence relations. Okay, let us see how it is. From the corollary, I can write a power p is congruent to a mod p. Okay, and it is given a power p is congruent to a mod q, right? This is from the corollary, and it is given that a power p is congruent to a mod q. It is given, right? Now I'll take up a power q to the power p. Okay, so from the corollary, this is nothing but a power q mod p. I hope you understood. Yeah, I'm applying this in place of a. I'm taking a power q. Okay, now a power q is congruent to a mod p. It is given a power q is congruent to a mod p. Okay, a power q is congruent to a mod p. I always forget to put. This is given. Now what is this? This is a power pq, okay, which is congruent to aq mod p, and aq is congruent to a mod p. Therefore I can write a power pq is congruent to a mod p, which means p divides a power pq minus a. A power pq, p divides a power pq minus a. Now again same thing I apply from the corollary, and it is given a power q is congruent to a mod p. I can write, this is 1, it's given a power q is congruent to a mod p, and corollary, from the corollary I can write a power q is congruent to a mod q. So now a power p to the power q is nothing but a power p mod q. From this I'm writing, okay. Now a power p is a power p is congruent to a mod q. It is given. So from the corollary, a power q is congruent to a mod q. In place of a, I am writing a power p. Okay. So a power p is to the power q is congruent to a power p mod q. But a power p is congruent to a mod q. So I am applying this over here. So a power pq is congruent to ap, which is in turn is congruent to a mod q. So this is the second relation. That means q divides a power pq minus a, which is the second relation in fact, right? So from 1 and 2 I can write pq divides a power pq minus a, which is nothing but a power pq is congruent to a mod pq. We now look at another milestone in development of number theory. Property says if p is a prime number, then p divides p minus 1 factorial plus 1. This statement was given by Wilson, and Wilson appears to have guessed this on the basis of numerical computation, but couldn't prove this because of the absence of notation for prime. How to express prime, it was not known at that time, so he couldn't prove this. But Lagrange gave the proof to this, and let us look at it. Okay. It says if p is a prime, then p minus 1 factorial is congruent to minus 1 mod p. proof for this was given by Lagrange. So you can check it out. If I have p equal to 2, then 2 minus 1 is 1. 1 is congruent to minus 1 mod 2, no doubt in that. If p is 3, then it is 2, which is of course congruent to minus 1 mod 3. Okay, so let us dismiss these cases and let us take those cases where p is greater than 3. Just take the situations where p is greater than 3. Suppose that a is one of the p minus 1 positive integers, okay, and consider the linear combination with a, linear congruence with a. Suppose a is one of the positive integer. Suppose a is one of the p minus 1 positive integers, and consider the linear congruence with a. Ax congruent to 1 mod p. Ax congruent to 1 mod p, where GCD of a and p is 1. In fact, they are relatively prime. Now, by the theorem, we know that congruence has a unique solution when modulo p is taken. So let us take a dash as a unique integer, okay. So there is a unique integer a dash in such a way that it lies in between 1 and p minus 1, which satisfies this linear congruence relation such that a dash is congruent to 1 mod p. Okay, since it is given that p is prime number, a has to be congruent to, a has to be equal to a dash if and only if this a is 1 or it is p minus 1. Because see, because p is prime, a should be equal to a dash. A is equal to a dash, that is only if either a equal to 1 or a equal to p minus 1. Because see, what happens is, if I consider a square is, if a equal to a dash, then a square is congruent to 1 mod p, right? Which is same as writing a square minus 1 is congruent to 0 mod p, right? And this is same as writing a minus 1 into a plus 1, which is congruent to 0 mod p. Now it means either a minus 1 is congruent to 0 mod p, or a plus 1 is congruent to 0 mod p. If a minus 1 is congruent to 0 mod p, then a is equal to 1. If a plus 1 is congruent to 0 mod p, then a is equal to p minus 1, right? Because a is giving you minus 1 mod p, positive value if you take, then it has to be p minus 1. Therefore, a is equal to a dash if and only if a equal to a dash if and only if either a equal to 1 or a equal to p minus 1. Now, so let us omit these solutions 1 and p minus 1. So the remaining values are 1 and p minus 1. Remaining set of possible solutions are 2, 3 up to p minus 2. Okay, I have omitted 1 and p minus 1. See, among this is one such integer I'm considering, okay, and I'm taking a linear congruence and I'm taking a dash in between these two, okay. And this a equal to a dash happens, if that is happens, then either a equal to 1 or a equal to p minus 1. Okay, so I'm just omitting these two now, so I'm left with 2 to p minus 2 possibilities. Okay, now I'm grouping these integers as a pair. Okay, like I'm taking a pair a dash in such a way that a is not equal to a dash, and their product when I consider a dash, which is congruent to 1 mod p. Okay, I'm grouping this into pairs a dash such that a is not equal to a dash and product a dash is congruent to 1 mod p. I'll explain this with an example, but at that time you'll understand. Now I'll complete the proof. Okay, when this happens, you're going to get, see, 2 to p minus 2 numbers are there. So I'm taking, at a time I'm taking 2. Okay, so how many such pairs will arrive? P minus 3 by 2 congruences will arrive, right? So these congruences I'm multiplying together. So it comes out to be, I'll tell you, see, 2 into 3 into 4 up to p minus 2 is congruent to 1 mod p. Why? Because see, each time I'm taking a pair, two numbers from this, okay, 2 to say p minus 4, 3 p minus 2, like that. Okay, so you are getting p minus 3 by 2 congruences and I'm clubbing all together, I'm multiplying them. Okay, at the end you are getting 2 into 3 into, either maybe they are paired like this, but when you multiply it won't matter, I'm going to get it like this. And what is this? This is nothing but I can say p minus 2 factorial, which is congruent to 1 mod p. Now what I do is I'll multiply this by p minus 1. Now I'm getting p minus 1 factorial is congruent to p minus 1 mod p. But it is in turn congruent to minus 1 mod p. Therefore, I can say p minus 1 factorial is congruent to minus 1 mod p. See, I'll tell you how this comes. I'll explain this by giving an example. Okay, suppose I have say p equal to 13. So this solutions will be in this set of integers up to p minus 1. So now what happens is, there are how many pairs? P minus 3 by 2 pairs. Okay, so 13 minus 3 is by 2 is 5. So you are going to get 5 pair of integers, each product of which is congruent to 1 mod 13, right? So how to set them? You have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? I have to combine them in such a way that I should get a into a dash is equal to 1 mod 11. So with respect to mod 11, I should get which two numbers I can combine in this. With 2, when I consider 2 into 3, I cannot take it as it comes out to be 6, so it won't be equal to congruent to 1 mod 11. 2 into 4, 8, again not possible. 2 into 5 comes out to be 10. 10 minus 1 it comes, so it cannot divide by 11. So let us take 2 into 7. It is, sorry, with respect to mod 13, I should check. Yeah, P is 13, no? I'm sorry. So 2 into 3 not possible, 2 into 4 not possible. Again 2 into 6 comes out to be 12. So again 12 minus 1, so it's not possible. 2 into 7 comes out to be 14. 14 minus 1, it is divisible by 13. So combining them, 2 into 7. One pair I got it as 2 into 7. Similarly with 3, I can take 3 into 8. But no, not possible. 3 into 9, so that 27, and it comes out to be 26. Yeah, it's possible. 3 into 9 is congruent to 1 mod 13. Like that, you can combine the pairs. 4 into 10, again that is also congruent to 1 mod 13. And 5 into 8. Then 6 into 11 is also congruent to 1 mod 13. So you got all these incongruences. Okay. Now you multiply all this. What you are going to get? 2 into 7 into 3 into 9 into 4 into 10 into 5 into 8 into 6 into 11, which is congruent to 1 mod 13. Which is nothing but 11 factorial is congruent to 1 mod 13. If I multiply by 12, then it is 12 factorial is congruent to 12 mod 13, which is nothing but minus 1 mod 13. So I'm using P minus 1 factorial is congruent to minus 1 mod P. I hope you understand. So application of this Wilson's theorem is to study quadratic congruences. Say ax squared plus bx plus c is congruent to say 0 mod n. Okay, where a is not congruent to 0 mod n. If that is the case, to study this Wilson's theorem helps. Okay, we'll take up the theorem based on this in my next video. Thank you.